This is the counting circuit. It counts from 0 to 9. It starts off with the NAND gate input. When the button is pressed, the NAND gate will produce a high because both inputs are low as current flows straight to ground instead of to the inputs of the NAND gate. This output then goes into RC1. It fills the capacitor, and when the button is released, the current slowly leaks out, giving us the duration of the circuit. This part of the circuit then feeds into RC2. In this part, we use a 104 capacitor and 3 more NAND gates to create the oscillation. As long as there is half the supply of voltage outputted by the capacitor, the NAND gate oscillator will produce a clock signal. This circuit is connected to a 4017 decade counter. The purpose of this chip is to use two main input pins, clock and reset, and divide the clock signal frequency by 10. The clock pin receives the clock signal, which is a series of pulses or square wave from the NAND gate oscillator. Each rising or falling edge of the clock signal triggers the chip to advance to the next output pin. When the pin is activated, it resets the chip counter back to the first output pin and starts counting again. It is then connected to the binary counter. This counter counts from 0 to 9 or 0 to 16 in binary and with 4 outputs and uses the 4510 or 4516 chip. This chip also has an up and down option for the counting, which is implemented in the final PCB. The last chip is the 4511. This chip processes binary coded decimal input to generate the segment control signals required to turn on the 7-segment LED display. It internally decodes the BCD input and activates the appropriate combination of output pins to light up the segments required to display a decimal digit. The 4511 chip provides 7 output pins labeled A, B, C, D, E, F, G, which correspond to the segments of a 7-segment display. Thank you for watching, and this is my final counting circuit in PCB with the 3D printed case.